Just takes the computer a second to wake up. Not very different from me, actually. This is what we were doing last time. Okay. Like I said, we're starting a new topic today, the last topic for the course. Maybe I'll just kind of look at the roadmap we've done so far. So we started off at the beginning of the semester looking at we thought of as the simplest case of ordinary differential equations, and that was linear first order ODEs, right? And so, well, the way that we proceeded from this to expand the types of things that we were looking at was to look at linear higher order ODEs, and really specific. We only looked at one specific higher order ODE, and that was second order. There was another path that we could have taken that we did not, because it's much more difficult, and that's to look at nonlinear ODEs. So we didn't spend any time looking at this. And so the third possible way that we could expand the types of things that we're looking at is to look not just at one ODE, but a system of interconnected ODEs. And so this will be our last topic, systems of linear first order ODEs. Right, in this direction. This is where we ended up the series. Okay. So what's a situation in which a system of ODEs might appear? One example is, we kind of draw a picture here. So let's say we have two masses here. We'll say the mass of this one is M1, one is M2. They're sliding on a kind of frictionless surface. They are attached to these walls by, you enjoying my drawing skills? They're attached to the walls by springs. All of these springs have their associated spring constants, K1, K2, K3. We'll call this equilibrium position X1, this equilibrium position X2. And movement in this direction to the right we'll consider positive. So that's the positive direction. And we'll also have applied to these some force that varies with time. Maybe not. We could have a force, or we could not have a force. And if we work out what this system should be in much the same way that we did before, what we'll get is two ODEs. So there'll be an ODE representing what happens to the first mass, and an ODE representing what happens to the second mass, but they will depend on each other. So how the forces that are applied to one mass will depend on the position of the other, and vice versa. Okay, so what does this look like? If we think of x1 as a function of t, then this is our mass times acceleration. and that should be equal to the force applied to this. And there's a force due to this spring K2 here. That's the spring constant K2. That depends on how far apart these masses are stretched. And so that's given by x2 minus x1. And then there's a force due to the spring 1, spring constant K1. And that's working in the opposite direction because it's determined by how far we're stretching in this direction. It will apply a force in this direction. And then there's the outside force F1. And we have a similar situation for x2. So we have force K3 times x2 for this spring right here. We have the middle spring applying a force on the other side. So it'll apply it in the opposite direction. It'll apply it in the negative direction. And then we have the external force F2. And you see that this equation, which is an ODE, second order linear ODE, it is, well, maybe it's not obvious that it's a linear ODE, but we can rewrite it in the standard form to show that it is. This one does not contain in the equation just x1. It contains x1 and x2, as well as this one. This one also contains x1 and x2. First of all, let's rewrite this so that it looks like a. So there's something that depends only on time. Actually, it doesn't. It depends on time trivially. It's because it's constant. It doesn't depend on x1 or x2 times the x1, and as well something that doesn't depend on x1 or x2 multiplied by x2. So that makes it linear. And then stuff that just depends on time. Similarly, we have K2 plus K3 times, I'm sorry, get that mixed up. K2 times x1 minus K2 plus K3 times x2 plus f2. Okay. So these are two linear equations. And they're, so these are, we'll call this a system. This is an example of a system of two linear second order ODEs. So this comes up very naturally in physical systems. There's more than one thing moving around that we want to keep track of. If you think of maybe like a tuning fork, you can think of this as a rod that has a certain vibration that it's naturally vibrates at. And if you think of you think of it as a line of pieces, and each of these pieces are connected together in a way that when one pushes up, it pulls this one up. So you can kind of think of them as being attached by springs. This is kind of like a model for a system like that. So this is a system of two linear second order ODEs. But the title of the section was first order ODEs. So what's the connection between these two things? Well, let's say any single higher order ODE can always be rewritten as a system of first order ODEs. And I want to underline system because we're not getting anything for free here. We take something that's more complicated, a higher order ODE, and we transform it into something simpler, a linear first order ODE, but there are several of them. So as a first example, let's look at this second order ODE. U double prime plus 1/8 U prime plus U equals 0. So this is a second order ODE. How could I write this as a system of first order ODEs? Well, I'll let x1 just be U, and I'll let x2 be U prime. So if we write this as, if we want to write this as a system of ODEs, first order ODEs, then this x2, of course, can be written, well, let's write in the opposite order. When we do first order ODEs, we tend to write the derivative by itself on the other side. So x1 prime equals x2. And then U double prime will be x2 prime plus 1/8 x2 plus x1 equals 0, or rewriting this in the form where we have just the first order derivative on the other side, on the left-hand side. x2 prime minus x1 minus 1/8 x2. And you can see it was pretty straightforward to make this conversion. Now, if we wanted to do something similar for this one, we could, let's actually, I'll leave that kind of as an exercise for you, but what we could do is take each of these second order ODEs and transform them into two first order ODEs. So we can transform these into a system of four. This system of two second order ODEs can be transformed into a system of four first order ODEs. This actually works in general for any higher order ODE. So let's say we had the arbitrary nth order ODE. So that's the nth derivative of y is equal to some big function of everything else. T, y, y prime, y double prime, all the way up to the n minus 1th derivative of y. So this encompasses all nth order ODEs, linear, nonlinear, homogeneous, non-homogeneous. All the possibilities are contained in this arbitrary first order or nth order ODE. So how do we transform this into a system of first order ODEs? Well, we say that x1 is y, x2 is y prime, x3 equals y double prime, all the way up to xn is equal to the n minus 1th derivative of y. So those will be our variables, our different components. And then what we get is that x1 prime is equal to x2, x2 prime is equal to x3, x3 prime is equal to x4, and so forth, all the way down to xn minus 1 prime is equal to xn. And finally, xn prime is equal to this big function on the right-hand side. So any function in terms of everything. So all of these look like a very different form than the last equation in the system. And in fact, this is a special case of a more general system. And so the way that we can write this more general system is x1 prime is equal to f1 of t y to yn minus 1. x2 prime is f2 t y all its derivatives up to the n minus 1th derivative. And finally, xn prime fn dy y prime y double prime all the way up to yn minus 1. And you'll see that this encompasses this. So it therefore encompasses or contains within it as a special case every single higher order ODE, linear or nonlinear. And in fact, by extension, by being able to rewrite each of these as a system of first order ODEs, it contains any system of ODEs, higher order ODEs. So this, when people study the more advanced theory of differential equations, they're basically studying systems like this. So this is stating the problem in such generality that it contains pretty much every possible ODE or system of ODEs that we might care about. Now, a solution to such a system, and we're talking about it now in the broadest generality possible, but we'll deal with specific cases soon. A solution to such a system is a collection x1 of t, x2 of t, all the way up to xn of t. It's a collection of functions Oh, I made a slight mistake here when I wrote this out. I mean to replace all of these y's, all these derivatives of y. These are the x's, right? These are the xi's. So this should be t, x1, x2, up to xn, and the same thing for the rest of them. So when we've done this, we've replaced all of these y and all of its derivatives with various individual functions. And we want a solution to the system. So it's a collection of these functions which satisfy all of the equations simultaneously. That's a very important and very strong constraint on the kinds of solutions that we can get. Now, if we're given such a system, you probably know where I'm going with this. Such a system along with x1 of 0 equals, we have to be a little creative with our subscripts and superscripts. So some constant x1, 0. Well, let's be even a little more general. We'll say we're getting it at our initial time t0. That's x2, 0 up to xn of t0 equals xn, 0. So these are obviously initial conditions. Is called n. Well, it's just an initial value problem, but in this case, for a system of ODEs. And maybe it's important. It's important to note. So maybe I'll put this right here, that we have a solution which satisfies all the equations simultaneously in some interval. So we want a collection of functions that satisfies the system, at least within some interval around our initial point. Okay. Now I'm just going to state this as the existence and uniqueness theorem. This is for systems of ODEs with initial conditions. So let each of the n functions f1 up to fn and the n squared first partial derivatives. So for each function, we're going to be looking at its derivative with respect to each of its possible variables. And then, of course, we have this for f2 as well. Maybe I'll write it like that. So all of the partial derivatives for f2 and then f3, and then finally all the partial derivatives for fn. So if all these things, we let them be continuous in some region R of the total space of all of our variables and t as well. So the t, x1, x2, up to xn space. Defined by the product of some intervals. Well, maybe what that means isn't quite so clear. So we're going to have an interval for t. We're going to have an interval for x1. Remember, in the single linear ODE case, we thought of this as being in the plane, right? There was the input t and then the output y, and we thought of this as being in ty space. Well, now this is some higher dimensional space. Harder to visualize, but well, it's not so hard if there's only two of them. That's just three-dimensional space. But once you get beyond that, it's kind of difficult. So if we have all of these functions and all their partial derivatives are continuous within some region of this higher dimensional space. And that space contains this point, t0, x1, 0, x2, 0, up to xn, 0. So it's contained in that region. Then there is an interval t minus t0 less than h. So some region before t0 and some region after t0. So at least for this some region in which there exists a unique solution. I'm just going to write it as x1 up to xn, reusing the variable names for the name of the solution of the system of differential equations that we wrote above, that also satisfies the initial conditions that we wrote above. So this is our version of existence and uniqueness for a system of first order ODEs, which really encompasses pretty much every ordinary differential equation that we'll ever care about. Pretty much anyone it cares about. All right. One important thing to note about this is that this region in which we have a solution that exists and unique could be, in fact, very, very, very small. Could be much, much smaller than the region R in which all of these functions are continuous and differentiable with their first partial derivative. The book doesn't prove this, and of course I'm not going to try to prove it either. The idea of the proof is basically the exact same thing that we had when we looked at the single first order ODE. Now, no, we'll stick with blue. If each of the functions fi is linear in the variables xi, xj, let's use a different subscript. So if there's no xi times xj, there's no xj squared, there's no x1 times x2 times x3, right? The stuff that's multiplied by the xj's is just something in terms of t, just what we meant by linear before. Then, well, that fi is said to be linear. Each of these fi's is said to be linear, and the system is said to be linear. So if each of these functions, I'll go back to this system that we had right here. If each of these functions is actually linear, a linear function in terms of x1, x2 up to xn, and the whole system is said to be linear, and these are the ones that we're going to care about. Otherwise, it's said to be nonlinear, obviously. No harm in writing it down, though. Otherwise, nonlinear. So if that's the case, if it's linear, then we can rewrite it in a special form, the linear form like we had before, and that is x1 prime equals t11 of t x1 up to p1n of t xn plus something just in terms of t, g1. x2 will be the p21 of t x1 up to p2 of n t xn plus g2 of t dot 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 all the way down to en1 tx1 up to en of t xn plus gn. Have either of you taken linear algebra before? Math 322, matrix algebra? No. Okay. I think Sydney, you said you're in engineering, and Sarah, I'm not sure. You're in engineering as well. Okay, so you will have to take this class at some point. That's good. We're gonna if you were familiar with matrices and matrix algebra, then a system that looks like this will be sort of crying out to you to use a matrix in the solution of these things, right? We have what looks like, well, it doesn't just look like it is. All of our variables here, right? Up here on the right-hand side as some linear combination. In this case, the coefficients in the linear combination are functions of t. So of course, matrices are going to come into this. Sorry, I don't know why computer is making so much noise. Actually, I do. I had Facebook open. Okay, there's a special form of the existence and uniqueness theorem for a system of linear ODEs. I'll just write theorem. If the functions Pij and I'll just write it out. I'll be a little more clear. P11 up to P1n, P21 up to P2n. Yeah, that's right. Pn1 up to Pn. And all of the G's, G1 up to Gn, are continuous on the open interval I, which we'll say goes from alpha up to beta. So if it's on some interval, this interval must contain T0. Let's write it like this. Some open interval alpha beta, which we'll call I, and we'll say it contains T0. It has to be in there somewhere. They left that out in the book. Then there exists a unique solution written exactly in the same way as the previous one. So I won't write it down again. Which satisfies the system of ODEs and the initial conditions all simultaneously. So I'll just say it satisfies the initial value problem. Oh no, they put the thing about T0 at the end. And this solution satisfying the IVP, it exists and is unique throughout the interval I. Underline that. That's an interesting fact. So in this case, in the linear case, we don't have a solution that only exists in some small confined. It does exist somewhere around our initial point, but maybe going out a little bit, it blows up to infinity or something like that. In this case, our solution will extend throughout the entire interval. Okay, so that's an introduction to the topic we're going to talk about. Now an introduction to the tool we're going to use to solve it, which is the matrix, or the plural is not written matrices, it's written matrices. Because it's Latin or Latin sounding. And that's how you do the plural with an X on the end in Latin. Okay, what is a matrix? Well, we've talked about this already, actually. So before we dealt with 2x2 matrices and we did a little work with those. So now we're going to extend this to larger matrices. So matrix is an n by m grid, where n and m are just arbitrary positive whole numbers of, and I'm going to put this in quotes, numbers. And maybe I'll start right off the bat by saying we're a little bit careful about what we mean when we say numbers. So there's a couple of possibilities that we deal with at this point in matrix algebra, probably all the matrix algebra you ever deal with. So there's two possibilities. There's real numbers, which is what we've tried to confine ourselves to up to this point. And then there's also the possibility of complex numbers, which we will deal with at in the course of doing things with matrices. Right. Okay, so what makes this a system of numbers? A system of numbers is that we can do addition, subtraction, multiplication, and division if it's not by zero of anything in these number systems. What sets this apart from other possibilities for numbers is, for example, the integers. If we think of this as our number system, then we can't do an arbitrary division by something that's not zero. For example, 3, and I'll use the old school symbol, 3 divided by 2 is not an integer. And so we can't do division in the integers like we would expect. If we also included in this fractions or the rational numbers, then we would have 3 halves, which is also a fraction. So in that case, this would be a type of number system that would work. We could do matrices, we could do matrix algebra with this kind of system. Because at a certain point when we do these things, we're going to have to do division. Okay, now this, using the rational numbers as our number system for matrices is of interest to people like me who study number theory, but for students of engineering, less interesting. Because you will want to include the irrational numbers as well. And once you take the rational numbers and you throw in the irrational numbers, you get the real numbers. And then when you take the real numbers and you throw in all possible solutions, all possible roots of polynomials, you get the complex numbers. And from that point, there's really nothing else that you can do to add stuff in that doesn't make things much more abstract than they already are. Anyway, those more abstract things that we could possibly do, those are also of interest to me as well. Okay, now before we go any further, I'm going to just go straight into some example matrices. We usually use capital letters And I'll just write out the grid of numbers. So I'm writing it in as columns. So it's these 3 columns. And then B will be 2, 1, 2, 1, minus 1, minus 1. One thing I'll say about linear algebra, so I taught this in the, I taught that in the spring. And it's very, very common, a very, very common reaction. If you've done very well in math throughout your whole life, or even if you've struggled, once you get to linear algebra, it's like almost like the subject matter is just changed. And it's very common to become very anxious and frustrated. So it's a good thing to see this now and let your brain, you start soaking it in. And then when you take the class, it's not going to be so hard. We're going to do easy stuff now. So these are 3 by 3 matrices. They're a square matrices. And that's, uh-oh, what did I do? Come on, zoom back. No, no, it was all going so well. All right. All right, 67%, pretty good. That's pretty close. Okay, square matrices are the most interesting to us, but if we look at rectangular matrices, we'll want to be able to say what their dimensions are. Oh, these are the dimensions of the matrix. It's 3 by 3. The first number represents the number of rows, and so these are the rows, the horizontal things, and the columns are the vertical things. So in this case, we have 3 rows by 3 columns. If I had done a rectangular matrix as my first example, it would have been clear to you which one was the rows and which one's the columns. But with a square matrix, they're both the same. It's kind of not clear. Okay. So we call it matrix algebra or linear algebra because I'm just thinking, actually, we've already seen where matrices can come from, right? We saw it as a system of linear equations. That's where we got them before. Okay, so we've talked about that. That's fine. So now we'll talk about things that you can do with matrices. And matrix algebra is kind of a hint of that. As long as the matrices satisfy certain rules, we can do things with them. So one of the things is just add them together. So if 2 matrices have the same dimensions, we can add them together. There's also a little proviso that they have the same number system. But in our case, it's okay. The rational numbers are contained inside the real numbers. The real numbers are contained inside the complex numbers. So we can just, when we do these things, we can say they're all in the complex numbers and just not worry about it. For other number systems, that doesn't quite work out. So if they have the same dimension, like these 2 matrices, they're both 3 by 3, then we can add them together. And we do addition just component-wise. So A plus B will be, the first entry will be in this top corner, 1 plus 2. Okay, now we're doing something fairly easy. We just have to match them up. So -2 plus 1, -1 plus 1, 0 plus 1, 2 minus 1, 0 plus -1 plus 2, 1 minus 1, 1 plus 1. That's what we get for A plus B. Now we can take something from our system of numbers and multiply it by the matrix. So let's say this is some number, a real number, a complex number, a rational number, whatever our number system is that we're using. And we multiply it by our matrix. We call this, when we just take a single number out of our number system and we do something with it. In matrix algebra or linear algebra, we call it a scalar, because we're going to scale everything by this amount. So if we say, well, let's just do it in general, and we'll do the specific, or yeah, sure, why not? Okay, so we just multiply it by every entry. We scale every entry by that scalar. So the first row will be alpha 0 to alpha, negative 2 alpha to alpha, 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 negative alpha, alpha. And if, for example, we had 3a, it would be 306, negative 6, 6, 3, 3 minus 3, 3. So that would be this matrix addition. This we might call scalar matrix multiplication. And then we have something, the thing that makes matrices really, really cool in comparison to the number field that we're talking about. And that's matrix multiplication. Now, the way matrix multiplication works, we'll do an example first. So A times B. I'll write it out first. 1, 0, 2, minus 2, 2, 1. And we've had a preview of this as well, but like I've said, yeah, minus 1. If you haven't seen this stuff before, the first time that you're introduced to it, it can be kind of a bit too much. So what we do to compute an entry, well, first of all, let's talk about the dimensions of the result. And we've seen this before. So this is 3 by 3, and this is 3 by 3. When you do a matrix multiplication, which I should write above because do a dividing line here. I wrote matrix addition, matrix multiplication. Right, we've got addition, we've got multiplication. It's almost like we've cooked up a new number system. The matrices are now the numbers, and we're doing addition and multiplication with them instead of just with individual numbers. Anyway, we take columns of the matrix on the right-hand side and rows of the matrices on the left-hand side, and we compute their inner product. We take matching entries, we multiply them together and add them up. So this will be 2 times 1 plus negative 2 times 1 plus 2 times 1. Now we should just compute this out and then erase that. And well, maybe when I say should, what I'm going to do. So because I want to save some space, I want to keep these matrices on the screen. So 2 times 1 plus 2 times 1, that's 4 minus 2. So what we get for our top left entry will be 2. Now to get the 1, let's do the 1 just to the right of it. That will instead be this column, since that'll be in the second column of the result in the product. And the first row, we take the second column of the one on the right, first column of the one on the left. And we kind of take this column, flip it on its side, set it right on top of that row, and add things up. So this is 1 plus 2, that's 3, minus 1, that's 2. Then we take this row, or this column, sorry, times the top row, and that's minus 1 plus 0 plus 1 is 0. And now we move on to doing this row. So that'll be 2 times 0 plus 1 times 2 minus 2 times 1, 0. 1 times 0, so negative 2 plus 1 will be negative 1. And then 0 plus 0 plus negative 1. I'm doing this very quickly. You can do this, you can practice this. You'll be ready for matrix algebra when you take it. 4 plus 1, that's 5 plus 2, 7. 2 minus 1, so that's 1 minus 1, so that's 0. And then negative 2 plus 1, negative 1. Okay. So this we write as AB, just like multiplication. This is A times B. And the interesting fact is that if we do B times A, in general, matrix multiplication is not commutative. So most of the time, almost all of the time, when you multiply two matrices, A times B, you will not get the same thing as B times A. 2, 1, 2, 1 minus 1 minus 1, minus 1, 0, 1, 1, 0, 2, minus 2, 2, 1, 1 minus 1, 1. Okay. Now what do we get for this? And it's going to be a little bit of work figuring this out, but it's 2 plus 0 minus 2, 0. Already we see that this is not the same thing, right? What does it mean? A equals B if and only if. What do we mean when A equals B? The corresponding entries. That's what we call each of the individual items in there, like a cell in a spreadsheet. The corresponding entries are equal. Just exactly what you might think equality means. Okay, then the one to the right of this is negative 4 plus 2, that's negative 2, minus 1, that's negative 3. 2 minus 1 minus 1, that's 0. Okay, now 1 plus 0, negative 2 minus 2, so that's negative 4. And you see when there are lots of zeros, these things become a lot easier to deal with. That's a fact that will actually become very important. So 1 plus 1, that's 2. 2 plus 2, that's 4. Negative 4 minus 2, that's negative 6. Plus 1, that's negative 5. And finally, 2 plus 1 is 3, plus 1 is 4. When you get a lot of practice, you can do these a lot more quickly. So what we saw from this is that AB definitely not equal BA. I can check it against the book. I didn't realize the book worked it all out. Hey, I got it right. Okay. Now, square matrices are a special type, and these are really the most interesting type of matrices. Maybe the second most interesting type is what we're called vectors. We've seen this before, but these are n by 1 or column matrices. So these are just they're matrices that are made just by a single column. And when we do, oh, maybe I didn't. Yeah, I didn't state this whenever we were doing matrix multiplication. The entries, the number of entries in a column here has to match the number of entries in a row here. In other words, the number of columns in the first matrix has to match the number of rows in the second matrix in order to do this matrix multiplication. Anything else is fine. So if we have an A by B matrix and we multiply it by a B by C matrix, everything is going to work out. These multiplications are going to work out. And the number of entries that we're going to get, or the dimension, the resulting dimension, is going to have the same number of rows as this one, because there's going to be a row for each of those rows. And it's going to have the same number of columns as this one. So what we're going to get is an A by C matrix. So you can think of these as, when you put the two matrices together, these two things have to match up, and they kind of Tetris together and disappear, and it becomes an A by C. And what does this mean? This means that we can take a vector, n by 1 column matrix. We have an example that we can use. Go with 1, 2, 3. We could take something like this. Now, normally we use capital letters to indicate matrices. We'll often use lowercase letters like X to indicate vectors, and then Greek letters like alpha, beta, gamma, so on. Lowercase Greek letters will represent scalars. Okay, how much time do I have? 2 minutes? Let's do an example of matrix vector multiplication. I'll write like this. One of the nice things about this recording is that we're going through this pretty quickly. You can just watch the recording later. 1, 0, 2, minus 2, 2, 1, 1 minus 1, 1. We'll multiply this by 1, 2, 3. Sometimes I write like what look like giant parentheses for a matrix. Sometimes I use square brackets. It's just all a matter of preference. Okay, anyway, matrix multiplication works out exactly the same way for this one. Maybe I will, we've got less than 1 minute left. I'll give this one to you. This one will be an exercise for you to try. If you want to check it with me tomorrow, you can do that. But I think for now I'm gonna stop giving you more information. And we have a little bit more to go over in the introduction to matrices. A lot of stuff. Okay. And then eigenvalues and eigenvectors, quick introduction to that. This is really a sort of like a very abbreviated version of the linear algebra class. Probably gonna have to cut some stuff out. And then after that, we will actually use matrices to solve systems of linear first order equations. All right, so it's exactly 11:20. Time that perfectly. I'll stick around for questions. Otherwise, have a good day. I'll see you tomorrow.